Cartesian product, also known as cross product, is denoted by the symbol x. It is used to combine two relations while performing two essential mathematical operations, that is addition and multiplication. But what exactly is getting added and multiplied? We'll get to that in a bit. Now, Cartesian product is usually used as an intermediate step in performing join operations. Now, since we're using two relations here, this is known as a binary operator or binary operation because we're using multiple relations here. Alright, let's understand this with an example. Hello learners, welcome back to Constant Learners. Today we're diving into an important concept in relational algebra, which is the Cartesian product, also known as the cross product. Stay tuned till the end of the video because we'll be discussing some very important characteristics of the Cartesian product that you would definitely not want to miss. Let's get started. Let's say we have two relations, relation A and relation B. Now both of these relations have two columns. Here we have ID and name, and relation B has ID and phone number. Relation A has three rows, 1, 2 and 3. And relation B has two rows or two tuples, 1 and 2. Now, when we take the Cartesian product of these two relations, that is, let's say A cross B, that is, every row of relation A will associate with every row of relation B. Let's say the first row, 101 John. First, it will get associated to this row here, and then it will get associated to this row here. Then we have Snow, 102 Snow. It will get associated with this row first, and then this row. And then the third row, 103 Sam, will get associated to this row here, and then it will get associated to this row here. That means every row in relation A will be associated with each row of relation B. This is the definition of Cartesian product. Now, we said that while performing Cartesian product, two important mathematical operations are being performed. So first, let's talk about addition. Now, in the output relation, what will happen? Total attributes will be. Attributes means column. How many attributes will be there in total? See, in this case, here we have two columns, 1, 2. So, two columns of relation A and 1, 2. Two columns of relation B. That means output will have 2 plus 2, that is total 4 columns, right? Then, tuples. Tuples means row. How many tuples will the output have? See, here we have 1, 2, 3 tuples, right? So, relation A has 3 tuples and here we have 1, 2. Relation B has 2 tuples. So, here we take the multiplication, that is 3 times 2 is equal to 6. So, the output will have total 6 tuples and 4 attributes, that is 4 columns and 6 rows. So, here is the mathematical operations being performed. The number of columns from both the relations are being added and the number of rows from both the relations are being multiplied, right? Now, what will be the output of this product? See, here we have the Cartesian product A cross B. In this case, the two columns from relation A are ID and name, and then we have ID and phone number, right, from relation B. Now, total number of rows here should be 6. So, we have 1, 2, 3, 4, 5 and 6 rows. If we look closely, first we have 101 John, which will get associated to both of these rows. So, we have 101 John with 101, 1, 2, 3, 4. 101, 1, 2, 3, 4. 101 John. Then the second row 102, 6, 7, 8, 9, 0. 102, 6, 7, 8, 9, 0. Right? Next, we have 102 Snow. It will get associated to both of these rows. So, 102 Snow, 102 Snow. We have the first row 101, 1, 2, 3, 4, 5. 102, 6, 7, 8, 9, 0. Correct? Then, third 103 Sam will get associated to both of these rows. 103 Sam with 101, 1, 2, 3, 4, 5. 103 Sam, 102, 6, 7, 8, 9, 0. Right? So, every row of relation A is being associated with every row of relation B. Alright? Now, in this case, we have two columns with the same name, that is ID and ID. Right? So, this is an ambiguity of cross product or Cartesian product. That multiple columns, there can be multiple columns in different tables that are having the same column name. And it can also have the same content. Right? The tuples may also be the same. Like here we have 101, 102, 103. Similarly, here also we have 101 and 102. So the tuples can also be similar. In that case, there can be confusion, and this is known as an ambiguity. So to prevent the confusion, what do we do is we add the relation name before the column name. That is, here, this is the ID. This is the ID from relation A, right? So we add A dot ID as the column name here. Okay, and this column ID is from relation B. So we get B dot ID as the relation name here. So we can associate the column names with the relations that they are belonging to. All right. So this was a very simple example. Let's take another example. Let's say we have a college database, and in this case, we need to create a list of all the students. That means we need the student's name and their corresponding courses, and we need their courses based on their major. So what are we basing our entire output on? Their major, and only include courses that have 4 or more credits, right? So their majors should be the selection criteria, and the credit has to be 4 or more. Now here we have two tables. We have the students table and the courses table. In the students table, we have 4 columns: student ID, name, age, and major. And here we have the course ID, course name, credits, and major, right? Now we need to combine these two columns so that we know which student is associated with which course. Correct? Now, how are we going to do that? The first thing that we will do is take the cross product or Cartesian product of both of these relations. So we are going to take students cross courses. When we take students cross courses, what will be the total number of columns in the output table? It will be 1, 2, 3, 4, 5, 6, 7, 8. So there will be total 8 columns in the output. And total tuples will be, here we have 1, 2, 3 times 1, 2, 3, 4. That is 3 times 4 is 12. So output will have 8 columns and 12 rows. Right? Now, this is the output of the cross product of students and the courses table. See, first student, here the first student is Alice, and she's taking computer science. She'll be associated with all of these 4 rows. That is data structure, calculus, quantum mechanics, and linear algebra. So here we have Alice with data structure, calculus, quantum mechanics, algebra. Next, Bob will be associated with again the 4 rows of table 2, and Charlie will also be associated with the 4 different rows of table 2, right? I hope that until here this was clear. Now the criteria is we have to list the students based on their major, right? So see, now Alice already has a major, that is computer science, right? Can she take a course from some other major? No, that is not possible, right? So here Alice has taken computer science, and data structures are also from computer science, right? So this row will be acceptable because the majors of both of these columns are the same. Next we have Alice with computer science, but here the major is mathematics. Can there be 2 different majors for one student? No. So this entire row will be eliminated. Correct? Next, Alice has computer science, but here she has physics. Again, this entire row will be eliminated. Then computer science with mathematics. Again, the entire row will be eliminated. Next, here Bob has mathematics, but here the major is computer science. So this entire row will also be eliminated. Again, here mathematics and here also mathematics. So this row will be acceptable. Here mathematics and here physics. So this row will also be eliminated. Here mathematics and here also mathematics. So this row will be accepted. Then Charlie has physics and here computer science. So this row will be eliminated. This row will be eliminated. Then here physics and physics. So this row will be accepted. Here again physics and mathematics. So this row will be eliminated. So in the output we have 4 rows. 1, 2, 3 and 4. How are we going to write the query? See, in the previous videos when we discussed select, project, union, set difference, I have explained you that when we have to select the entire row, which operation are we going to use? The select operation, right? So in this case, what will be the condition for the select operation? The condition will be that student's major should be equal to the course's major. And that condition is being satisfied here. The student's major are same. Mathematics, 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 physics, and physics. And how are we writing the query? Sigma. Sigma means select student major is equal to course major. But the second criteria is that they should include courses that have 4 or more credits, right? So here in this case now, we only need to select the majors that have 4 or more credit. In this case, we only have 2 rows. One is for Alice and the other one is for Charlie, right? So now, again, we need to select this entire row and this entire row. So if we are selecting the entire row, again, we are going to use the select operation. So the criteria here, where we have student major is equal to course major, here we are going to add one more criteria, that is credits has to be greater than or equal to 4. And it will come with the AND operation, that is this one, right? AND operation. In case of AND operation, both the conditions have to be true. Only then the final result will be true. So here we are selecting students major is equal to course major and the credits are greater than or equal to 4, right? Now, in case of the question, that is the query, we only have to list the students and their corresponding courses. That means we don't want all the columns here. The columns that we are getting here are 8 columns, 1, 2, 3, 4, 5, 6, 7, 8. We don't want all 8 columns. We only want the names and we need the courses, right? So we need these 2 columns. Now we've already studied that if you're going to select the columns, which operation are we going to use? We are going to use the projection operation denoted by pi, right? So the query will be project. Which columns are we projecting? Name and course name, and the entire query will be the same because now from this table we are selecting the entire thing, right? So in this case, we are using the entire query but with the projection operation, and when we are doing that, we got the name and the course name. So this is our final output, right? So when we need data from 2 different tables, first thing that we do is take the cross product of both of these tables and then use the required conditions to project the desired output. I hope that this was clear. Now there's another example that you need to do by yourself, and in the end we are going to discuss the characteristics of cross product or Cartesian product. In this example, it says that it is a hospital database and we need to list all the patients that each doctor is treating. That means we need the doctor's name and the patient's name. That is, Dr. Smith is treating which patients from here. Dr. Johnson is treating which patients and Dr. Williams is treating which patients. Now in this case, the condition that we are going to use is the specialty. Okay, so we're going to use this as the condition that is helping us to connect the doctors with the patients. All right, I think you can write this query very easily. If you still don't understand how to do it, kindly watch the previous example once again. Take a minute, try to do it by yourself. Then I'm definitely sure that you'll be able to write the query on your own. And if you still don't get it, I'll make sure to leave the answer as the first comment. Now finally, the characteristics of Cartesian product. The Cartesian product in relational algebra is an operation that creates a new relation by combining every tuple from one relation with every tuple from another relation, right? And thus it is a binary operator. It is denoted by the symbol X. We've already discussed this. For example, if we have R, relation R and relation S, and we need to take the cross product, we write R cross S, right? Next, if a relation R has m tuples and relation S has n tuples, then the output relation will have m times n number of rows. Alright, then the resulting relation contains all attributes from both input relations. Now, if there are duplicate attribute names, they are typically renamed to avoid ambiguity. And I already told you how we do that. We use the table name dot the name of the column. Then the Cartesian product by itself doesn't typically represent any meaningful data. It's often used as an intermediate step in performing more complex queries. For example, to perform join operations in relational algebra. Now, due to its potentially large output size, the Cartesian product can be computationally expensive and thus it is usually avoided in practical database operations unless it is extremely necessary. Alright, so that's all for today's video on Cartesian product in relational algebra. After we've done the entire course on relational algebra, should we go to structured query language or should we discuss the university questions on database management system? Let me know your thoughts in the comment section. If you have any questions that you think I should focus on, then don't forget to share them in the comment section. If you found this helpful, don't forget to like, subscribe, and hit the notification bell. See you in the next video where we will explore more fascinating concepts in database theory. Thank you so much for watching.